Hi everyone, thanks for listening to this talk. Today I'm going to be talking to you about the feasibility of super resolution reconstruction for speech real-time MRI. I have nothing to disclose. Real-time MRI is an emergent imaging technique that's commonly used to measure movements, and one such application is that of human speech, which allows us to image features such as the tongue, velum, lips, and epiglottis within the vocal tract. In order to measure such rapid movements of the tongue and lips, a high temporal resolution is often required. Current techniques, using spiral imaging, can have some blurring and artifacts from corruptions due to off-resonance as well as rapid motions. In these images, we can see examples of this where rapid tongue motions cause blurring as well as artifacts. The question that this work poses is, can we use deep learning to super-resolve speech real-time MRI? The motivation for this is that by collecting fewer case-space samples and having shorter readouts, we can potentially improve the temporal resolution as well as the errors due to off-resonance. The dataset used included 58 subjects, 34 of which were used for training, 12 for validation, and 12 for testing. This dataset comes from a recent work submitted to this conference, abstract number 0438, which is an open dataset for speech real-time MRI. In order to generate low-resolution and high-resolution pairs for training, an iterative constrained reconstruction with a temporal finite difference was used on both the full spiral case-space data as well as truncated and zero-padded case-space data. This image shows how case-space was truncated for a 16x downsampling scale. The zero padding in case-space allows for the same pixel size of the input and output images, allowing us to train a residual network. I refer to these input zero-padded case-space images as sync-interpolated images. The network trained on was the Very Deep Residual Network, or VDSR, which is an architecture that has found a lot of success in traditional camera-based imaging for super resolution. This architecture consists of several chain, convolutional, and rectified linear unit blocks, and it trains a residual image such that when added to the input sync-interpolated image, it creates a predicted high-resolution output. The VDSR network was run on 3 downsampling scales. It's important to note that in the abstract submission, the scales were noted as 2x, 3x, and 4x, but this nomenclature has changed to 4x, 9x, and 16x to keep the downsampling scale to match the relative case-space area. Since we are using spiral imaging, using only a 4x in downsampling means that we only need 37.6% of the relative data acquisition time, which shows that we could massively improve the temporal resolution for future data using this approach. Here's some initial results with 4x downsampling scale. As you can see, the super resolution images do a pretty good job of reconstructing features including the lips, the velum, the epiglottis, and the tongue. At this frame, we can see that the epiglottis is properly reconstructed in both the ground truth as well as the super resolved image. However, there is some extra blurring in the super resolution image, which comes from the blurring in the sync-interpolated image at the epiglottis area as well. For this top subject, we can see that the lip closures are properly reconstructed in the super resolution image, as shown also in the ground truth image. But in the sync-interpolated input image, we see that there is a lot of blurring at these boundaries, and it's hard to tell where exactly the lip closure is. In this frame, I'll analyze the super resolution response at higher scales, including 9x and 16x. In the 4x case, we see that the epiglottis is properly reconstructed and matches the ground truth. However, as we increase the downsampling scale and go to 9x and 16x, we see that the epiglottis starts to get completely lost and look completely unrealistic at the 9x and 16x scales, making it pretty unusable if analysis of the epiglottis is required. Quantitatively, we can see that the VDSR network performs quite well on mean squared error, peak signal-to-noise ratio, and the structural similarity index. And as the downsampling scale increases, the errors increase for both sync interpolation and super resolution, but the super resolution network performs consistently better than its sync interpolated counterparts. To conclude, super resolution reconstruction is definitely feasible and shows quantitative improvements over traditional interpolation. However, more analysis of the data and potential changes in network design are needed to tailor the response for specific speech applications that require specific areas of the vocal tract to have a more accurate reconstruction. Thank you for your time.